So in this video, we're going to go through chapter 3. Okay, so hopefully having the textbook up on the screen is helpful. I don't know if that makes sense or not. You guys can certainly give me some feedback. And I've also got a notepad here to the right that hopefully we can do some examples if we need to. Okay, so after chapter 2, which was mathematically complex, okay, we're moving on to chapter 3, which is more straightforward. So we're starting several sections on different strategies for solving problems. Okay, so the first one we're going to do is brute force, and we'll also talk about exhaustive search. Okay, the brute force basically means, I like to say, it's like if you've got a problem, you hit it with a hammer until it resolves itself. Okay, there's no finesse here. Okay, it's just, as it says here, it's a straightforward approach to solving the problem. It's directly based on the problem statement and the definition of the concepts involved here. Okay, so for example here, they give, and do I have the highlighter going? Maybe. Is that the highlighter? It's not the highlighter. I can highlight that. Move that way. Okay. So if we're looking at this problem of computing a to the n, okay, for a non-zero number, a and a non-negative n, okay. One way to do this. So here's our definition of exponentiation. Okay. We're not going to do anything fancy. Okay. We're not going to try to make the problem anything different than that. Okay. We're simply going to compute that by multiplying it n times. Okay. We'll find out later that there's actually a different approach to doing this, which is surprising in some ways. Okay. So these usually are not clever or efficient algorithms. They're usually quite the opposite. Okay. But what they are is pretty straightforward. Okay. You're just going to do whatever is simple and just keep doing it. Okay. Until you get the solution that you want. Okay. But it can be easy to deal with. Okay, so in some cases, it doesn't matter what the efficiency is. You have a small problem set, okay? Or it could be that for some problems, there's no better way to do it. And we'll get to some of those problems later, okay? So one of the things we're going to talk about a lot in this class is sorting, okay? Just the idea of being able to sort a list of things. The reason we do that is because having something sorted, as we saw in the last problem set, makes a lot of operations such as searching easier, okay, much more efficient, okay. So sorting is a big deal. We'll talk about that a lot. As far as the brute force goes, there are a couple of searches or a couple of sorts here that we're going to talk about, okay. So this one, we're starting with a selection sort. So with it, we basically go through the entire list of elements, okay, and find the smallest one. Okay, and then we're going to return that or move that to the first position, swap it out. Okay, and that's it. So to switch over to here for a second, our friend the whiteboard. Okay, so if we had 7, 4, 6, 3, 10. Okay, the idea would be basically that we're going to go through the list, every element, okay, and we're going to keep track of the smallest. Okay, so, and we'd start this, let's say the smallest is 7. Is this one smaller? Yeah, so now the smallest is 4. Smallest is still 4. Smallest is 3. Smallest is still 3. Okay, so the smallest is going to be 3. We would then swap the 3 and the 7. Okay, and we would know that this is sorted. Okay, the next time through, we would go and find out the 4 is the smallest, nothing would move. So the 3 and the 4 are sorted. Okay, and then 6, 7, 10. Okay, the next time through, we would see that 6 is the smallest, so no switches needed there either. So the 3, 4, 6 are all sorted. Okay, with the 7 and 10 over there. And in fact, the rest of these are sorted as well. So we would do the 3, 4, 6, 7. That's done with the 10 over here. And then finally the 3, 4, 6, 7, 10. Okay, then that would be done. Okay. So that's what the idea of the sorted list looks like. Okay. Let me get to this if we need it. Not that, that. There we go. Okay. So that's what it does. So let's look at the pseudocode here. Let's make sure we understand this. So our algorithm here is selection sort. It's going to take an array from 0 to n minus 1. It's going to sort this by selection sort. The input's an array. The output is another array. Okay, remember that these have to be orderable elements. If you have an array of cats, unless you have a good way to sort or order cats, you're not going to be able to sort it. Okay, so but what's going to be the output is going to be a non-decreasing order on the array. Okay, so we're going to start with this outer for loop. Okay, we're going to say for I is I, again, this is the equal or gets or assign. So for I assign the value of 0 up to n minus 2, n is the number of elements you have, do, okay? So we're going to let them set the minimum equal to the first element, okay, the first time through. And then we're going to go through and go from j is equal to I to 1, sorry, I plus 1, we're going to start 1 over, to n minus 1, do, okay? We're basically here going to swap the minimums here, okay? We're going to give the new, sorry, it's early. Here we're going to calculate the new minimum, okay? So if the current element is smaller than the first element, okay, it's the new minimum, basically. And then when we're done, we're going to swap those positions, okay? And it gives us an example here, okay? It's also giving the summation here of how this efficiency works, okay? The number of times it's executed. It depends only on the array size. There's not a better or worse for this one, okay? Because we're going to check everything no matter what. So this is going to be our number of comparisons. We're going to call this comparison here is in the innermost loop, okay? And we're going to go through first from the outer loop goes from 1, or sorry, from 0 to n minus 2. The inner loop goes from I plus 1 to n minus 1, okay, of 1, and then we can solve that based on, and again, I'll do a separate video. There've been several questions on the summation problems, but make sure you remember that in the back of the book, there's some summation formulas, it seems like, okay? So this turns out not to be a super great algorithm as far as efficiency goes, okay? So you see here, it's pretty much at n squared. Okay, this will turn into an n squared as far as the efficiency goes. But you know, it's not horrible. Okay, what is horrible? So horrible that oftentimes we don't even teach it is a bubble sort. Okay, so a bubble sort works, again, same input, same output. Okay, and it's going to have the same number of comparisons, but the difference is, okay, so let me just show you. I guess I could do it over here. If we have 5 to, I don't know, 7, 1, 6, whatever, okay. What the bubble sort does, it's going to compare the two, okay, and it's going to move, does it move the smaller? Because it could go either way. Okay, so the largest element is going to go to the right every time, okay? So it's going to compare these two, the 5 and the 2. It's going to rewrite that as a 2 and a 5, okay? It's then going to compare the 5 with the 7, okay? And it's going to keep the 7 bigger, okay? It's then going to compare the 7 with the 1, okay? So the 1 goes there, the 7 goes there, okay? And then it compares the 7 with the 6. It'll put the 6 there and the 7 there, okay? So just like with the selection sort, we call it the bubble sort because the 7 is bubbling up to the top, okay? Just like the selection sort, we're going to have to go through and do it however many times, you know, for n, we're going to have to do n squared either way. But the problem is we're doing all these memory swaps, okay? Where with the selection sort, there's only one swap per trip through the loop, okay? And with the bubble sort, there's a bunch. You swap all the way, okay? And then with the second time through, so we can now say that 7 we know is sorted, okay? So we can bold that, okay? We would then compare the 2 and the 5, okay? They're in correct orders. We compare the 5 and the 1. The 1 moves there, the 5 moves there, okay, we would compare the 5 and the 6, and they're in the correct order. 7 stays there, okay? We would then say that is correct, okay? We would then do the 2 and the 1, which we would reorder those. The 1 and the 2, okay? We would do the 2 versus the 5. They're in the correct order, okay? We would then say, and even though we're sorted here, we don't know it from our algorithm, okay? We would then compare the 1 and the 2, okay? Bold. The 1 and the 2, and they're in the correct order. So we bold that one, and then we would be done, okay? So there's just a lot more going on here, okay? It's not a good sort. So to look at what the code looks like, we've got it over here, okay? And you know, it's pretty straightforward code as far as that goes. And we're going through, it's in the same class. It just has a lot more key switches, okay? So that's that section. And there's the homework, which I'll put up at some point, okay? So the next section talks about sequential search and brute force string matching, okay? So the sequential search means, again, being brute force, we're just going to keep looking till we find something, okay? And that's really all we're doing here. So if we look at this sequential search algorithm here, so our input's going to be an array of n elements and some search key k. And the output is going to be the index of the first element in our array whose value is equal to k, or -1 if there's nothing, okay? So we're going to start with this a of n, okay? We're going to assign it to our key value here, okay? Then we're going to set I equal to 1, and then we're going to go through I as long as I does not equal to k. Then we're going to keep searching item by item, okay, until the end. That's basically all we're doing here, okay? So again, if we have letters, we have numbers or whatever, we're just going to search the first item, search the second item, search the third item, all the way through, okay? So with that, your efficiency there is going to be linear. It's going to be n, right? You have to touch every element at least one time, okay? So not great, but it gets the job done. And if you don't have sorted data, it's all that you have, okay? Something else we're going to talk about a lot is this idea of string matching, okay? So if you have a string of n characters, which we're going to call the text, and a string of m characters called the pattern, the question is, you want to find a subset of the text that matches a pattern, okay? So the subset of n that matches m, what we're looking for here, okay? Want to return that index. So the brute force algorithm then is pretty straightforward. And again, for all these, most all these, we're going to find better ways to do it, but we're just going to line up the beginning of the pattern to see if it matches, okay? So we've got A, B, A, F, G, whatever we got, okay? If that's our text and our pattern is AF, okay? We start by lining up AF here, okay? Is that it? Nope. We're gonna move it one over. Let me switch this to a font that's mono-spaced to make life easier. Okay. So we're here. Is that it? Nope. Is that it? Nope. Is that it? Nope. Is that it? Yep, we're done. Okay. So nothing fancy. We're just going to keep going, keep hitting it with a hammer until we find it. Okay. And then again, if our search turns something else like AZ, we're going to start at the beginning, keep searching all the way through. Only then would we know that it can't be. Okay. So here's what this algorithm looks like here. Okay. Again, we've got this for loop here, we've got a while loop there. Okay. Searching through every time. Okay. And again, because of the embedded loops here, this feels like n squared. Okay. And I don't know if they say that, but that's where we're at on that. So It does have a best case, worst case. Okay, yeah, that's correct. It does show that. Okay, but there are better ways to do string matching. Okay. 3.3, a couple of kinds of problems that I like. The first one is a closest pair problem. Okay, so with the closest pair problem, what we're saying is that you have a set of points on the plane. Okay, so we've got n points on a plane. We're 2 dimensions now, although it can be done in however many dimensions that you want. Okay, so the points could be anything. Okay, as the book says here. And we're wanting to find out which of the 2 points are close together. Okay, so we get a formula here where this is just the distance formula. Okay, right here with our Cartesian plane. That's all we're doing here. So again, this probably makes sense, and this gets ugly, unfortunately. What am I sharing? That's a good question. I don't think I was sharing any of that. That's really unfortunate. Now I've lost the ability to change anything. I don't know why. I don't know why I don't have a menu. Okay, not sure how much of that wasn't there. Sorry about that. But you could follow along in the book. That's exactly what I was doing. I'll try to make sure I'm not doing that again. Sorry about that. Okay, anyway, the closest pair problem. Again, you have points on the Cartesian plane, and you want to see which 2 are close together. And we just have our regular points formula here for 2 points in the Cartesian plane. Okay, so to see this visually, go over here for the whiteboard. Okay, clear all this. Okay, so you've got your XY axis, which are normally straight in that, but you get the idea. You just got a set of points wherever you have them. Doesn't matter. And the question is, which 2 points are the closest? Okay. Again, we're going to have more reasonable kinds of solutions to this, but the brute force is simply going to be testing them all. Okay. So start at the furthest point on the left if you want. Check this distance, and then that distance, and then that distance, and then that distance. Okay, and then that distance, and all the other distances. Okay, check all the distances from every point to every other point. Okay, and then see which one is the smallest. That's our brute force solution here. Okay, so what this looks like in algorithm form, okay, is this. Okay, we're again finding the distance between the 2 closest points by brute force. So we're going to get a list P of n points. Okay, the output's going to be the distance between the closest pair of points. We're not tracking here, for example, which 2 points are the closest. We're just tracking the ones that is the smallest thing here. Okay, so here we've got our D being set to infinity just because it doesn't have a value yet, but we want it to be there later. We've got for I going from 1 to n minus 1, okay, and then from J going from I plus 1 to n. We have the stagger here with the plus 1, so when we check point 1 versus all the other points, when we go to point 2, we don't have to do point 2 back to point 1. We've already calculated that one. Okay, so we're doing it for, if there are 10 points, we'll have 9 comparisons the first time, then 8, then 7, then 6. Okay. So then inside of those loops, we're just doing the point formula from up here. Okay. And again, one thing that we should do, we didn't do this on the problem set. We should, if we use a sort or we use a length or whatever function we're using, go ahead and put a comment as to what that is. Okay. Then we're going to return the D. Okay. So for this one, the basic operation here is going to be the square root calculation. Okay. And it's going to go through and this one again, we see 2 loops. This is going to be n squared. Okay, that's our gut feel, but it shows how it happens, just to give us some practice on that. Okay, these are non-recursive algorithms, so we're doing summations, not limits, which is good. Okay, also the convex hull problem. Okay, I like this one as well. This one, what we're looking for here. Okay, we're looking for And again, it says some people believe this is the most important problem in computational geography or geometry, which is a big field. Lots of applications to that. Okay, so it talks about some of the reasons here, but we have a set of points in a plane are called convex. I'm down here for this definition. If for any 2 points P and Q in the set, the entire line segment with the endpoints belong to the set. Okay, so in other words, the set is going to contain all the points and then all the lines that you can draw. Okay, we'll see some examples in the book of things that are not that way. Okay, so we also define a convex hull then down here is a set of S points in the smallest convex set containing S. Okay, the smallest here means that the convex hull of S must be a subset of any convex set containing S. Okay, so if we look here, we see that this section are all going to be convex sets, right? Because from every point in here, it's not going to let me draw. From every point to here, we can draw to every other point without leaving the set. Okay. Whereas these sets on the right, if I go from that point to that point, I assume you're seeing my cursor there. Okay, that you're going to leave the set basically. Okay. One way to think of this is that if we were to take our points and have a board with the Cartesian grid out on it for a Cartesian plane and put a nail in at every point, if we put a rubber band around the whole thing, then that rubber band would form the convex hull. It would be the smallest set that contains all of that. Okay, so that's the idea behind a convex set. Okay, and then there's a picture here of these points and then what the convex hull would be. Okay, again, if we have any bigger area, which we could draw, any bigger shape, it's going to be a hull, but it's not going to be the convex hull. Okay, so the convex hull problem then is the problem of constructing a convex hull for a set that you're given. Okay, so these edges of the vertices here, okay, we're going to call these the extreme points. Okay, it's a point that is not in the middle point of any line segment that has endpoints in the set. Okay, so if we could have a line segment that contains it, that it's a midpoint, then it's not going to be a point. Okay, so again, we're going to solve this by brute force here. Okay, so these extreme points have properties that the other points don't have. Okay, that we're going to talk about that later as we find better solutions. Okay, but for right now, we're just going to look at the brute force manner. Okay, so this is not as straightforward as the other one here. Okay, but the point here, okay, is that we're going to look at all of, we're going to draw a line between 2 points. We're going to see if all the other points lie on the same side between these 2 points. Okay, so if we're going to go back up to our example here, okay, if we draw a line through P7 and P2, okay, is it true that all points are on the same side of this line? And it's not. P6 is not. Okay, so P7 to P2 is not an element of the convex hull. But if you look at P1 through P3, draw a line through that, extend that line, then you see that all of the elements are to the right. Right may not be the right word. They're all to the same side. Okay, so our strategy here, we're going to start with P1 and P2, draw a line here. Is it in the convex hull? It's not. And then P1 through P3, is it? It is. Okay, P1 through P4 is not. P1 through P5 is. P1 through P6 is not. P1 through P7 is not. Okay, we would then move to point 2 and then so forth. Okay, and that would allow us to determine which ones are in the in there or not. Okay, and it turns out this algorithm is big O of n cubed. Okay, because there's a whole lot going on. Okay, We're going to get to more efficient algorithms for this. And they don't give us an algorithm for this, but that's the basic idea, okay, of this one. Exhaustive search. Okay, the exhaustive search, it's a brute force way to a combinatorial problem here. Okay, so something like this is going to be one of the more famous problems that we're going to talk about in this class. That's called the traveling salesman problem. Okay, the traveling salesman problem, it says basically that you have a salesman who has to go through N cities, visit cities, each city exactly one time, and return back to where they started. Okay. The problem will be represented typically by a weighted graph where each edge will have a distance weight. Okay. The point is to find the most efficient path through that. Okay. If you do that, then basically this gets recast as finding the shortest Hamiltonian circuit, which is just another way to say exactly what the problem says here. Okay. So there's not really any way besides brute force to figure this one out. We'll get to this more later, but that's the idea there. There's another famous problem we talk about, the knapsack problem. And there's a more example of the exhaustive traveling salesman problem here. The knapsack problem is that you have a knapsack or a backpack, whatever you want to call it, of some given capacity W, okay? And then you have an item, you have N items of known weights, W1 through Wn, and values that correspond V1 through Vn. And then big W is a capacity. The question is, how do you pack the backpack to maximize the value? Okay, so how do you figure out how to put in the right number of items, okay, to maximize V without going over the big W, okay? And that's the problem there. And it's, again, one that if you look at here's solving it on page 118, where if you have nothing in your backpack, then the weight's 0, but the total value is also 0. If you have just the first item, and we have our item weights and values listed up here, all through the permutations here, okay? And again, many of those are not feasible because the weight would exceed the weight limit, okay? So that's what that problem looks like. There's also an assignment problem, which is another category of problem. With the assignment problem, we're basically looking at, you have jobs, you have people to do them. Each person has a cost for every job, okay? And you can one person can only do one job. So you have to line up the person to the job, okay? So it's not as simple as picking the cheapest person for the job, because the same person could be the cheapest on several jobs, okay? So again, you just have to go through, and here's an example of doing the cost of all of the different permutations of that, okay? Again, we're going to find more efficient ways to solve this later, okay? And then finally, I think it's the last section of this chapter, we have these exhaustive search ideas here, the depth first search and the breadth first search, okay? So the depth first search, okay, it starts, again, we're talking about a graph. If you're unfamiliar with graphs, let me do a quick graph primer. We're not talking about graphs like graphing a function. We're talking about the very specific definition of graph here. And you can look it up in Wikipedia and find all kinds of stuff. So a graph here, so a graph G is going to be a set of V vertices, okay, connected by E edges, how we typically say it, okay? So the set of vertices is going to be something like this. They're going to have a number, okay? These would all have, you know, I'm not going to number them because it's bad enough as it is. Well, I kind of need to, though. If we have 1, 2, 3, 4, 5, okay? So V would be, in this case, the set 1, 2, I really need my mouse or my pencil, 3, 4, 5. And then E would be whatever connections there are between them, okay? So E could be, in this case, 2, 3 is an edge. 3, 5 is an edge, and so forth. Okay. And then if these have values here, then it's a weighted graph. Okay. So the idea behind the depth first, now we need a few more lines here for this to make sense. With depth first, okay, was gonna make that black, but life goes on. With depth first, the idea is to get away from the vertex as quick as possible. So we do 1 to 2 and then 2 to 3 and search that way, okay, for the depth first. The breadth first would do a 1 to 2 and then a 1 to 5 before it moved on, okay? And that's the only real difference there. Let's go back to seeing that more formally here. Okay, so again, it starts at an arbitrary vertex, mark it as visited, and then it's going to go to an unvisited vertex that's adjacent to the one it's currently in. Okay, and then if there's a tie, it's just going to figure it out. Okay, it's going to keep going until it hits a dead end, then it's going to backtrack to the vertex that had some unvisited ones. Okay, so the depth first search here. Okay, we can construct this depth first search forest. Tells us how to do that. Okay, so here's the pseudocode for the depth first search itself. Okay, how we're going through that. Okay, then we also have the breadth first. The breadth first is we're going to check all of the edges from one vertex before we move forward. Okay, and we can also have the breadth first search forest here. Define it this way, and there's the algorithm for that. Okay, and I think that is it for this chapter. Yes. Okay, so hopefully this made sense. If there are better ways to lecture this, I'm not sure that there are, but we'll see. I mean, I could always just do it on a whiteboard the whole way and write out the examples, or who knows. So you can give me some feedback on if this is working for you or not. Okay, and I will go ahead and it's Saturday, so either today or tomorrow, I will go ahead and post the next problem set. Okay, if you haven't seen it yet, I have posted the problem set solution video for problem set 1. Okay, so you can take a look at that. Okay, so that's all I've got. So again, let me know if you have any questions about this chapter. Next week, we'll go on to another strategy in chapter 4.